So to finish up this lecture 12, I want to cover a very important topic, which is known as the topic of equivalence relations. And this is a topic that we've talked about in some sense already. We define an equivalence relation R on a set A is a reflexive, symmetric, and transitive relation. So it's a relation that has the properties of reflexivity, symmetry, and transitivity. These are super important in constructing new mathematical sets, and also, understanding additional, properties of relations and connectivity. And I'll illustrate this by giving a number of different examples of this. Using our notation from before for element A is related to B, if we have an equivalence relation, we say that two elements A and B are equivalent under an equivalence relation if A is related to B under that equivalent relation. And one of the important things to note here is that in equivalence relation, in some sense, partitions a given set A into all of the subsets of elements that are equivalent to one another. So this is the definition of an equivalence class. So if R is an equivalence relation, on a set A, the equivalence class of an element A is the set of all other elements, or all elements equivalent to A. And the notation that we use here is a box, and sometimes we put an R in the subscript. If it's known what the relation is, we just put the box. Sometimes you can omit the relation R symbol if it's known exactly what this is, but this specifically is a set of all S in A such that A comma S are in the relation, or a set of all S in A such that A is related to S under the equivalence relation R. And notationally speaking, we can talk about a given representative of an equivalence class. So for instance, if B is some element of the equivalence class AR, then B is called a representative of the equivalence class. Of A, element A. And it's important to point out that a given equivalence class is just a subset of A, therefore it's an element of the power set of A. And what's important about representatives is that there's nothing special about any particular element chosen as a representative of the equivalence class. So you can directly go through and say, do mathematics and study the properties of a given element or a given representative of any given equivalence class. So before I jump into the examples, what I want to do is talk about a very important theorem which has to do with how equivalence relation partitions a given set. So if we let R be an equivalence relation on a set A, the following statements are equivalent for any two elements A and B of A. We have that A is related to B, or A comma B is an element of R, is equivalent to the statement that the equivalence class of A is equal to the equivalence class of B, which is the same statement as saying the equivalence class of A and B are not disjoint, so their intersection is non-empty. And the proof of this theorem can be broken into three parts. For part one, we're going to show that statement 1 implies statement 2. So assume that A is related to B, and remember that we need to show statement 2, which is that the equivalence class of A must equal the equivalence class of B. So in order to do that, we have to show that the equivalence class of A is a subset of the equivalence class of B, and we need to show that the equivalence class of B is a subset of the equivalence class of A. So to show that the equivalence class of A is a subset of the equivalence class of B for any x that is in the equivalence class of A, we have that A is related to x under this equivalence relation by definition of the equivalence class, and by assumption, our assumption is that A is related to B. We're assuming 1. We have that A is related to B, and by symmetry of the equivalence relation, we then have that x is related to A, and we also have then that A is related to B from our assumption. So this step is by symmetry, the symmetry property. And the last step then is that by transitivity, if x is related to a and a is related to b, then x must be related to b, which means that b is related to x by symmetry, and this means that x is an element of the equivalence class of b. This proof right here is very, very similar. So I'm not even going to go through, but I recommend going through and kind of understanding both. If you understand this proof, then this proof is almost the exact same thing, word for word. So the second part of this proof, part 2, we're going to prove that if 2 is true, then 3 must be true. We're going to assume two, which is that the equivalence class of A is equal to the equivalence class of B. By definition, A is not empty because A is an element of the equivalence class of A by definition. Specifically, this is coming from, let's say, by a specific property of reflexivity. So I can put by reflexivity, which is one of the things that defines an equivalence relation. The equivalence class of A will always be non-empty because it will always at least contain the element A itself. Therefore, the intersection of A with B is going to be a non-empty set. And the reason is because A, we're assuming 2, which is that the equivalence class of A is equal to the equivalence class of B. So these two sets are equal to one another. We've shown that the equivalence class of A is non-empty, therefore, because these two sets are equal to one another, right, they share all of their elements in common. And then because they're not empty, this means that they can't be the empty set. Their intersection can't be the empty set. So this concludes part 2. And then lastly, part 3 of this proof is showing that 3, so if statement 3, then statement 1. And if we do this, we've successfully completed our loop, and we have that each one of these statements is equivalent. Because if I show if this, then this, if this, then this, and if this, then this, I have that all of these 3 statements are equivalent to one another. We'll start by assuming 3, which is that the intersection of 2 given equivalence classes for 2 given elements is non-empty. If this is the case, then there exists an element C in the set A such that C is an element of the intersection of the equivalence class of A and the equivalence class of B, which means that C is an element of the equivalence class of A and C is an element of the equivalence class of B. So A is equivalent to C, and B is equivalent to C, which is the same thing as A is equivalent to C and C is equivalent to B by symmetry. And then by transitivity, this then means that A is equivalent to B, or related to B. And so we have that 3 implies 1. And this concludes the proof of that statement. And what's really neat here now is that what this is showing is that a given equivalence relation takes a given set A, there's just going to be a figure here, and it cuts that set A up into disjoint equivalence classes. And the idea here is that if you have a bunch of, say, elements in the set A and an equivalence relation on the Cartesian product of A, this equivalence class is partitioning your set into a whole bunch of disjoint subsets, each of which represents a specific equivalence class of a given element A. So this is our set A. This could be the equivalence class of some given element of A, where A is one of the elements in this equivalence class. This is a super important idea because the idea now is that we can go through and use this to actually construct many given sets that we normally use and kind of sometimes use without really thinking of the actual mathematical definition of those sets. So it's important to point out here that these partitions, right, if we kind of number these partitions by the elements and you form the union over all elements A and A of these equivalence classes, we're going to result in the actual individual set itself. So the union of every single one of these equivalence classes gives you the total set itself. But individually speaking, these individual equivalence classes are disjoint from one another. So they split A into disjoint subsets of elements that are equivalent under the given equivalence relation. And we can give a precise definition to this. We say that a partition of a set S is a collection of disjoint subsets of S that have S as their union. because so if A is not equivalent to B, the equivalence class of A and the equivalence class of B are going to be the intersection is going to be the empty set. They're disjoint from one another. So each of these equivalence classes are going to be disjoint, and their union directly is the entire set A. So this is exactly a partition. And the idea here is that we can actually use this to define a very important set called the quotient set for a given equivalence relation. So if we consider the set, we call the notation quotient set, we use the division symbol. A divided by the relation R, sometimes called A divided by tilde. This is the set of all equivalence classes for all elements A in A. So if I take the union of all of these equivalence classes up in this figure here, and we consider the collection of each equivalence class, this collection is essentially the quotient set. So for this picture, the quotient set is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 elements to it, even if A is an infinite set. And that's a very important thing to point out and see. So with this new machinery now, we can go through and discuss a number of different examples. First huge example that we're going to really see a lot of in the next coming lectures is what's called modular arithmetic. You can put a firm mathematical basis for modular arithmetic. So if we call A to be Z instead of integers, and M is a positive integer, and we define the relation R to be that A is related to B, so the order pair A comma B is related to A is related to B if the proposition M divides A minus B is true. A little bit of notation here. Remember that M divides A minus B means that there exists an integer K such that A minus B is equal to K times M. That's how we read this statement right here. And it's also very important to point out here that this is actually, this relation is sometimes said that A is congruent to B mod M. So this means A is congruent to B mod M. So be careful here, because I don't want you to get confused. This is not logical equivalence, and we already used the triple equal sign for logical equivalence, but in a somewhat unfortunate turn of events, this is also very much used for congruence relations. So you have to be very, very careful when we're talking in terms of integers, and you see a mod M here. This statement right here means A is congruent to B mod M, which means that M divides the difference of these two values. So this relation R is an equivalence relation. And this can be shown relatively simply. For transitivity, we have that, and I guess I'll probably start with reflexivity because it's probably the simplest one of the three to prove. For reflexivity, you have that A is related to A because M divides A minus A, or M divides 0 for any M in the positive integers. Proof of symmetry is a little bit longer, but it's not that bad. We assume that A is related to B. We need to show for symmetry that B is related to A. If A is related to B, then M divides A minus B, which means that there exists a K in Z such that A minus B is equal to K times M. But if we multiply this by -1, that means there exists a K such that B minus A is equal to negative K times M. Or B minus A is equal to L times M, which means that M divides B minus A. Therefore, B is related to A. So this is a symmetric relation. And lastly, for transitivity, the congruence relation is going to be making sure that A is related to B and B is related to C. If this is true, that means that M divides A minus B and M divides B minus C, which means that there exists K and, or I'll say P and Q, just to not confuse it with these values here. So there exists P and Q in Z such that A minus B is equal to P times M and B minus C is equal to Q times M. If we add these two equations together, the B's cancel out and we get A minus C is equal to P plus Q times M, or A minus C is equal to R times M, which means that M divides A minus C and A is related to C under the equivalence relation. Therefore, R is an equivalence relation. And what's important to look at now is a visualization of the equivalence classes of this equivalence relation. So what I've graphed out here is the line of positive and negative integers. And what we're going to do is we're going to look at everything that's equivalent to 0 under this equivalence relation, and we'll choose m equals 5 here, and that's all these blue points right here. 0 is equivalent to 5, or is congruent to 5. 5 is congruent to 5 mod 5. 10 is congruent to 5 mod 5. 15 is congruent to 5 mod 5. 1 is congruent to 1 mod 5. 6 is congruent to 1 mod 5. Negative 4 is congruent to 1 mod 5. So it's all these red dots right here. All the purple dots are 2. So 2 is congruent to 7 mod 5, which is congruent to 12 mod 5, and so on and so forth. Three is congruent to 8 mod 5, congruent to negative 2 mod 5, and so on and so forth. And then lastly, 4 is congruent to 9 mod 5, congruent to 14 mod 5, and so on and so forth. So what you can see here now then is that this is a very nice visualization of the equivalence classes, and it turns out that we have 5 equivalence classes for this equivalence relation when we're dealing with modular arithmetic mod 5. In general, we'll have m equivalence classes. And so if we go through, and we directly look at, say, the quotient space for the space A mod the equivalence relation, or Z mod the equivalence relation, this is the set equivalence class of 0, the equivalence class of 1, the equivalence class of 2, and so on and so forth, all the way up to the equivalence class of m minus 1. And this is in general, the general case. For the example where m equals 5, Z mod the equivalence relation just ends up being the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, equivalence class of 3, and the equivalence class of 4. But this is the correct set to do modular arithmetic in. For instance, if I take any two values, like we'll say an element x that's in the equivalence class of 3 and an element y that's in the equivalence class of 4, then x plus y is going to be an element in the equivalence class of 3 plus 1, 2, 3, 4. So it'll be the equivalence class of 2. So this shows us exactly what the correct logical basis is for the idea of modular arithmetic, or clock hand arithmetic, that we talked about before. For instance, a clock, the hours on a clock has m equals 12 in 12-hour time, and m equals 24 in military time. And this example is going to be at the heart of really what we're going to be studying when we get into number theory. Specifically, it'll be very closely applied when we talk about RSA cryptography. It's kind of the basis, in number theory is the basis for a very successful cryptographic method for guaranteeing that messages are sent securely. And so for the next example, I'm going to talk about the mathematical construction of z, or the integers. And this is a very, very neat example because it gives us a way of actually, putting a mathematical definition down for the integer z. And the idea is that up until this point, we've only exactly constructed the natural numbers. And within the natural numbers, the only operation that it really makes sense to define is addition. We can define addition as a map between two input natural numbers that gives us a new natural number. We don't have subtraction, so we need our equivalence relation to only use addition in the natural numbers. And sure enough, we can do this directly. If we say that our set A is a set of ordered pairs of natural numbers, and we define the equivalence relation R to be the set of ordered pairs A comma B in the Cartesian product of A with itself, such that, and remember, if A and B are both elements of A, then A is an ordered pair of natural numbers, and B is also an ordered pair of natural numbers. So we say that A is related to B if A1 plus B2 is equal to A2 plus B1. And I'm not going to go through and prove that R is an equivalence relation, but we proved it in the homework. And it's a relatively straightforward proof. What's really neat here is we can really kind of visualize this as follows. And I'll open up a plot of this. So this is a picture showing the Cartesian product of the natural numbers with itself, and if you draw all elements that are equivalent to one another under this equivalence relation, specifically we consider all elements that are equivalent to 0, 0, you get all of these elements. So 0, 0, 1, 1, 2, 2, 3, 3. These are all of the ordered pairs that are equivalent to 0, 0. So this is an equivalence class, this set of elements. Likewise, if you plot out this equivalence class right here, this set of all elements that's equivalent to 1, 0. So 2, 1 is equivalent to 1, 0. 3, 2 is equivalent to 1, 0, and so on and so forth. And I've plotted some of these out right here. Likewise, plot out 3 more of the equivalence classes from this equivalence relation. So if you look at this, you kind of think about this, what this is looking like, and what is exactly true is, if we call the equivalence class corresponding to the 0, 0, if we call this the integer 0, in each one of the equivalence classes in the positive direction, we number 1, 2, 3, 4, 5, and so on. In each of the equivalence classes in the negative direction, we number -1, -2, -3, and so on and so forth. what we're seeing is that we have a direct correspondence with the integers, both the positive and negative integers in 0. So these equivalence classes of this equivalence relation are directly corresponding to the positive, negative, and 0 integer, which is very, very cool. Furthermore, if you want to give meaning to something like an integer addition equation, like negative 1 plus 3 is equal to 2, this is entirely possible to do using these equivalence classes. We know that if x is in an element of the equivalence class in for the element 0, 1, then it's equivalent in some sense to negative 1. And we take an element y in the equivalence class of 3, 0, right? Because negative 1 is represented by this equivalence class, 3 is represented by this equivalence class, and you add any representative element from these two equivalence classes, the addition here, we're going to do component-wise addition. You end up getting a new ordered pair, which is 3, 1, which is under this equivalence relation equivalent to 2, 0. And so we have an exact expression of this mathematical relationship, which is amazing, right? What it means is that these equivalence classes can be used to take a basic set like the natural numbers and construct a more complicated set that directly maps to the positive integers. So we know z as the set 0, 1, negative 1, negative 2, positive 2, and so on and so forth. What we've just shown is that z is directly isomorphic. Set theoretic is an isomorphism to the set A cross A mod the equivalence relation, or the quotient set of this equivalence relation, because 0 is equivalent to the equivalence class of the ordered pair 0, 0. 1 maps to the equivalence class of 1, 0. Negative 2 or negative 1 maps to the equivalence class of 0, 1. Negative 2 maps to the equivalence class of 0, 2. Positive 2 maps to the equivalence class of 2, 0. And so on and so forth. Where each of the corresponding elements here, you can see, is directly mapped to its equivalence class. This is a very, very neat example showing the power of this idea of quotient spaces, or quotient sets, and equivalence relations. And for the last example, I'm going to discuss the mathematical construction of the rational numbers. Up until now, we only have the divides relation acting on integers, but we, informally speaking, think of the rational numbers as the set Q of all ratios P over Q where P is an element of the integers and Q is an element of the positive integers. We can make this more precise and accurate by expressing this set as an equivalence relation on the Cartesian product of these two sets. So if we let A be the set of all ordered pairs of integers and positive integers, and we define the relation R to be the set of all ordered pairs in A cross A, such that, and remember, if A is an A, it's an ordered pair A1, A2, where A1 is an integer, A2 is a positive integer, and B, then if B is an A, B is also a listing of ordered pairs. We say that A is related to B if A1 times B2 is equal to A2 times B1. And the last problem of your homework was to prove that R is an equivalence relation. So I'm not going to go through and prove that here, but I want to visualize what this means, and specifically I want to visualize the equivalence classes of this equivalence relation. So this is a picture of Z cross Z plus, or the integers Cartesian product with the positive integers. And sure enough, we can go through and look at the equivalence classes here. In this case, these purple points are everything equivalent to the ordered pair 1, 1. So 2, 2 is equivalent to that, 3, 3 is equivalent to that, and so on and so forth. And everything equivalent to 1, 2 is all of these points right here. Everything equivalent to 2, 3 is all of these points right here. This is the equivalence class of 2, 3. Everything equivalent to negative 3, 5 is all of these points right here. Everything equivalent to 2, 1 is all of these points right here. 3, 2, all of these points right here. Negative 5, 3, all of these points along this line right here, and so on and so forth. And right, to try to list out all of these just like before would be impossible. But hopefully you can clearly see that what we've done here is actually construct the rational numbers, these equivalence classes of all fractions that are equivalent to one another. And this is exactly what it ends up being. For instance, for the 1, 2 equivalence class, we have 1, 2 is equivalent to 2, 4, and so on and so forth. And this is true for all of these. But what we've done is essentially used an equivalence relation and only multiplication on the integers, right, to actually define what we mean by these rational numbers. And you can see this a little bit more clearly when you look at how to actually do addition. Let's say, for instance, we take some x, it's an element of the equivalence class of a comma b, and we take some y, that's an element of the equivalence class of c comma d. The correct way to add x and y, so for instance, to add a and b plus c comma d, in the rational numbers is now not direct addition like it was for the integers, but the ordered pair A comma B plus the ordered pair C comma D is going to give you a new ordered pair that is the ordered pair AD plus BC comma BD. And this is how we define the addition of these ordered pairs in this relationship. This is directly mathematically equivalent to the idea of adding two rational numbers, A over B plus C over D, and bringing them to common denominator, in which case you get a new rational number that's AD plus BC divided by BD. And I used some Python code that I wrote up to actually display this out for the first few examples in this set of ordered pairs. And sure enough, right, you can clearly see that this equivalence class is equivalent to the rational number 1. This equivalence class is equivalent to the rational number 1/2. This equivalence class is equivalent to the rational number 2 over 1, and so on and so forth. This is a very nice picture kind of illustrating this idea and exactly what we've done. And it provides a formal basis now for discussing the rational numbers.